Right after the 90-degree RF pulse switches off, an MRI sequence begins. The targeted proton's magnetic vectors snap down onto a flat horizontal plane. Here, longitudinal magnetization on the vertical z-axis is entirely empty, registering at absolute zero. Simultaneously, on the xy plane, transverse magnetization reaches its physical maximum. These precessing nuclei rotate in phase, generating a sinusoidal electrical voltage measured by the scanner. But this high-energy state is unstable. The signal immediately begins to decay as the entire system tries returning to resting equilibrium. That return to equilibrium doesn't happen through one single decay process. It is driven by two completely distinct physical mechanisms happening simultaneously. The first mechanism governs the vertical z-axis. This is called spin lattice relaxation. The second mechanism controls the horizontal xy plane. This is spin-spin relaxation. Even though they happen simultaneously, their timelines are strictly independent. The speed at which the z-axis recovers has nothing to do with the rate at which the xy plane decays. To tell the difference between tissue types like fat and water, we have to stop thinking about a single measurement of decay and instead track these two orthogonal vectors independently. Let's isolate the vertical z-axis to examine the spin lattice mechanism. On the right is an abstract representation of the surrounding molecular environment, or lattice. As the nuclei precess, they bump into surrounding molecules. Through these collisions, they shed absorbed RF energy into the lattice grid. Every drop of lost energy causes the vertical z-axis to steadily recover its longitudinal magnetization, tracing an upward exponential curve. To measure the speed of this recovery, physicists use a specific time constant known as T1. By definition, T1 is the exact duration it takes for the longitudinal magnetization to recover to 63% of its maximum value. The speed required to reach that 63% mark depends entirely on the physical size and kinetic energy of the surrounding molecules. Consider large macromolecular structures, like fat and protein. Because these molecules are massive, they have very low innate kinetic energy. That makes them highly efficient sponges, perfectly suited to absorb the shed energy from the tumbling nuclei. That rapid, efficient energy absorption forces the z-axis to recover quickly. Therefore, fat is classified as having a short T1. Look at small fluid water molecules. Their incredibly light size and rapid thermal motion makes them terrible at catching and absorbing the shed energy. Because the energy transfer is so inefficient, the z-axis recovery drags on. Water has a predictably long T1. At the extreme end, perfectly rigid structures like bone and calcium are the absolute worst at absorbing this energy, stretching their T1 times out even further. The physical size and thermal motion of a tissue's molecules dictate how fast it crosses that 63.
This is the domain of spin-spin relaxation. During this process, absolutely zero energy is transferred from the nuclei to the surrounding molecular lattice. Instead, the individual nuclei magnetically interact with each other, slightly altering local magnetic fields. These tiny local variations cause some nuclei to spin slightly faster and others slightly slower, destroying their unified phase coherence. As they fall out of sync, their net transverse signal exponentially decays towards zero. The constant we use to measure this transverse decay is T2. T2 is the precise duration required for the transverse magnetization to drop down to 37% of its starting value. Molecular structure plays a role too. Rigid solids and large fat molecules create severe local magnetic variations, forcing rapid dephasing and a short T2. Water is in constant rapid motion. This movement physically smooths out the local magnetic variations, sustaining phase coherence for a very long T2. But a major complication arises when we move from theoretical quantum mechanics to the physical reality of a clinical scanner. The actual electrical signal recorded by the MRI coils is known as free induction decay, or FID. This graph charts that decay. The shallow curve is the theoretical, ideal T2 decay, but the actual measured FID signal drops to zero significantly faster. We call this steeper curve T2 star. The culprit is the main B0 magnetic field of the scanner itself. Unavoidable inhomogeneities in that external field artificially force the nuclei to dephase faster than the tissue's innate properties dictate. The raw MRI signal is corrupted by its environment. To isolate the true T2 tissue signature, scanners run specialized spin echo sequences to delete external interference. We can apply this dual mechanism model directly to concrete clinical data, specifically using relaxation times measured at a standard field strength of 1 Tesla. This table compares the relaxation times of fat and water to show how these theoretical models behave in practice. Fat reveals a massive divergence in its vectors, a 250 millisecond T1 recovery paired with a rapid 80 millisecond T2 decay. Water exhibits massive values on both fronts, an incredibly slow 3000 millisecond T1 recovery and an equally long 3000 millisecond T2 decay. This data establishes an unbreakable rule of biological MRI physics. T1 time is always longer than T2 time in human tissue. There is exactly one mathematical exception to this rule visible on the chart: pure water. Pure water is the exception because it completely lacks the complex molecular lattice structures found in tissue, which allows its T1 recovery to exactly match its T2 decay. Understanding these exact numeric constants allows us to look past the raw physics and actually build diagnostic images. By precisely manipulating the scanner's sequence timing to capture either that 63% recovery point or that 37% decay point, a radiologist creates the visual contrast necessary to see inside the body. Mastering the orthogonal independence of the T1 and T2 vectors provides the exact physical baseline required to interpret pathological changes in human tissue.